Okay, last time we talked about parsing, and I gave you two dynamic programming methods to do this parsing in polynomial time. One of them was a bottom-up parsing technique, okay, which was CKY. Where is CKY? Okay. CKY says that, okay, I am going to make a table, parsing table, like this, okay, and each of these boxes, this is a half table, triangle table. Each of these boxes will represent word groups, okay. This one represents groups between 0 and 1, that is book. This one represents this one represents the words between 2 and 3, etc. And in this sense, going from left to right and from bottom to up, I fill in that table one by one. So I don't in this way I avoid any redoing of the same thing over and over again, repetition of the same thing. And also the other nice thing is this can recover any ambiguous three representations of the same sentence. Okay, so this was bottom-up approach. We talked about that, and then after that we had another one, early parsing, top-down approach. This one say that I will start from the top. I will start from the star symbol or sentence. Then I will say that with the sentence could be a noun phrase, verb phrase. Now I am expecting a noun phrase then, etc. So I am going to modify my rules using this not notation. There are three cases: completed constituents, in progress constituents, and predicted constituents. Okay, this is okay, completed, this is in progress, and this is predicted. That's the early parsing. And early parsing, like the CKY, it is a parsing technique. It is dynamic programming based technique, but other than the different from CKY, it doesn't require you to write your rules in binary form, right? It can be any type of grammar. Okay, we looked at both of those, and we said that, of course, we don't solve ambiguity problem. Ambiguity is always there. We just said that I can give you two different parsing of the same sentence if the sentence is ambiguous in two ways. Okay, so the way we deal with ambiguity is a little bit different. For some reason, as soon as we read the sentence, we understand it in one sense. We ignore the many other senses. Okay, so most of the time, and we are right, but many times, especially if we try to write sentences in a hurry, okay, read sentences in a hurry, then there might be times there might be times that the sentence is ambiguous. For example, there were lots of ambiguous sentences in this questionnaire that we asked the undergrad students to. Okay, most of the sentences I don't understand coming from the students. For example, what do you understand from this one? Okul içi sosyalleşme problemi. Too much sosyalleşme. Okay, it can mean many things, right? So I need context, but if somebody doesn't know our case of our university's case, we wouldn't understand. I mean, is it the sosyalleşme problemi, sosyalleşmenin az olması mı, çok olması mı? We don't know what that is. What else? I think there was a question about exams. Let me find it. Ne anlıyorsunuz bu cümleden?
Haftalar süresi hocam.
2 hafta.
Onu mu anlıyorsunuz? Ben hocalar 3-4 saatlik vize yapıyor diye düşünmüştüm.
Bir haftada bitmemesi.
Okay, so you got it. So that means that ambiguity is with me. Okay, so this kind of stuff is common to all languages, especially if you don't share the same context. Well, I don't share the exact same context with the students, because I don't make many exams. I just make 2 of them, and I thought that my exams are too long. Let's say that there are many exams and it is going on for 2-3 weeks, and maybe we should do it in the same week. So ambiguity again, it is all common for all languages. So that was the end of this chapter. Then we started talking about dependency parsing, and I guess we stopped at that point. Okay, if I do this like that, good. Okay, dependency parsing. We said that not all languages are suitable for constituency-based parsing. Okay, what is constituency? Constituency says that the words come after each other following some rules. Okay, when you combine them, they become sentence elements. Okay, sentence components. The cat cuddly by door. Okay, they are all each a word, but when you put them together, the cuddly cat is a noun phrase. By the door is a prepositional phrase, right? And then you can combine them, noun phrase, prepositional phrase. It makes another noun phrase, the cuddly cat by the door. Well, the English sentence structure is suitable for this kind of an analysis. That's what we call the context-free grammar analysis of the sentences. But not all languages are built this way. Okay, some of them are very different. And sometimes you don't need this kind of grouping to do something. This is maybe sometimes overkill. Okay. So this is one approach. Constituency, phrase structure grammar. Okay. So I can do this. And the other approach is different. The other approach says that, okay, let's find relationships between the words in a sentence. Okay, some words are more important than the others. Okay, and if I find that those words, and if I can find the relationship between those words and others, then that's a parsing. That's how we understand the sentence structure. Okay. So if the sentence is ambiguous, of course, there would be different types of connections, and ambiguities will be there. We are not going to solve the ambiguity problem. We looked at those before. I'm going to skip them. Okay. So the second way of looking at the sentence structure is dependency grammar. Okay. We say that syntactic structure consists of relationships between lexical items, and normally binary asymmetric relations. It's binary. There is a relationship between these two. It's binary, 2 of them, and it's asymmetric. Why? Because there is a relationship between this and this. It is nominal subject, submitted, nominal subject. Okay, and submitted. This is the object of it, right? Submitted object. And this is the auxiliary. Submitted is a verb, and this is the auxiliary part of it. So it is not symmetric. There is no relationship between verb to submitted, auxiliary, but submitted to verb, it is auxiliary. Okay, and these relationships are shown by the arrows. Sometimes they change the direction of the arrows. Some people show the arrows the other way, but in this example we are going to show it this way. Okay, those are arrows, those are single directional relationships, and they are typed. Okay, and what we say that we say that okay, the arrow connects a head, okay, with a dependent. Submitted is the head, this is the dependent. Bill is the head, this is the dependent. Okay, Kansas is the head, off is the dependent. So for each relationship, for each binary relationship, okay, there is a head and dependent. And usually dependencies form a tree. What does it mean usually? So in some cases, maybe there might be more than one. For example, it is not this case, but you could have this. So this is not a tree anymore, it's a graph, right? So there is more than one way of going from one node to another one. Okay, rare cases I am not going to show you any of them, but it could happen. So we are going to assume that these dependencies form a tree, connected acyclic single head. Okay, so this is a very old theory actually. Arabic linguistics people, linguistic scientists, they did this in the first, before the first millennium. Okay, and other people did that kind of stuff, dependency grammar. So I'm going to skip it. And this is an example of discussion of the outstanding issues was completed. Completed is the main head of the sentence. Root is something that we add extra, add a fake root, so every root is a dependent of precisely one other node. Okay, so root is the fake head. Completed is dependent of that one. It's the main verb of the sentence. Was is the auxiliary part. This is the punctuation of the completed. Then I have this one. This is the subject of the sentence, and etc. It goes that way. And I have a few examples here. Do you think there are any Koreans in Miramar? Okay. Do you think there are any? So the root is here. Verb is this one. Think is the main entry of the sentence. But all of the stuff, they are connected to each other, one way or the other. This one says that, okay, this is my subject, nominal subject. Okay, you think. This is the auxiliary of the verb, and this is the punctuation, and this one is the C comp. I guess it means a complementary sentence. There are any Koreans in Miramar, right? Another sentence, C comp. So I am composing a sentence with another one. Okay, and this one has. Okay, this one has its own subjects and objects and everything. Okay, so this is called dependency parsing. And dependency parsing is very common for some languages, and like the context-free parsing, there are algorithms to do that. Since there are algorithms to do that, there should be some kind of a tree bank to give us some dependency parsing examples. That's where we are going to look at. That's where we are going to look at how we perform, how our algorithms are performing with this annotated data. Okay, so dependency parsing, conditioning preferences. So we say that, okay, these are not exact rules to follow. They are just preferences. This is what happens actually. For example, bilexical affinities. Okay, discussion and issues usually they happen together. They are usually dependent on each other. One is a head, the other one is the dependent. Okay, they happen together. Okay, that is plausible. Dependency distance, usually dependency arrows are short. Okay, mostly within nearby words. Okay, it is rare in a sentence that the dependency is far away. Okay, intervening material dependencies really span intervening verbs or punctuation. Okay, so the usually you are not going to see this is where is the verb? Verb is here, right? Nobody goes over the verb. No arc is going to go over the verb. See verb and verb and verb and punctuation. Okay, so that's what it means. Intervening material and valence of heads. How many dependents on which side are usual for the head? Okay, usually sentence, the head of the sentence is just one verb. What I'm saying is that there are some rules for the dependency parsing, and you are not going to see any. You are not going to see any. If this happens, this is it. If this happens, this is it, kind of thing. It's kind of soft rules. Some of them will be violated. Some of them will be ignored. But generally, we follow these rules. So you might be wondering, how am I going to make the dependency parsing then if the rules are not definite rules? We are going to see it in a few minutes. Okay, so the dependency is parsed by choosing for each word what other word is dependent of, including the root. Once you find this verb, the main head of the sentence, then for this one, find the relationship between this word and the others. If there is, then mark it. If it is, then we don't do it. Okay, so usually you don't have this kind of dependency trees, dependency relationship. See, there is an intersecting arrow. This talk, bootstrapping, and give tomorrow is intersecting. This is called non-projective dependency parse. This usually doesn't happen. Okay, this usually doesn't happen. So how do you prevent it? You will say, I will give a talk on bootstrapping tomorrow, right? If I move tomorrow out, so there wouldn't be any intersection, right? There wouldn't be any intersection. Okay, but I change its position. Tomorrow is there, so there is the non-projectivity in this case. By the way, if you have such a grammar, if you can say this, okay, you cannot write a context-free grammar for this one. Context-free grammars, I cannot form. See, this one and this one is forming a constituency. This one is forming a constituency. You cannot mix your constituencies in each other, okay, in context-free grammars. Dependency parsing allows it, but we call that non-projective grammars. In Turkish, we have lots of non-projective stuff all over the language. Okay, so that's the definition of the projectivity. No crossing dependency arcs when the words are laid out in the linear order with all arcs above the words. Okay, how do you fix the projectivity problem here? Who did Bill buy the coffee from yesterday? Make it non-projective. Grammatically better form.
Bill buy the coffee from who?
No. From whom did Bill buy the coffee yesterday, right? That's the non-projective. That's the projective. This one. This is better. Yes. Okay, but dependency theory normally does allow non-projective structures to account for displaced constituents. Dependency is parallel to context-free grammars. Context-free grammar tree must be projective. Okay, so methods of dependency parsing, let's look at that one. There are many ways of doing this dependency parsing. Of course, if you do it, if you try to find all kinds of possible dependencies between each of these words. If I have n words, there are n times n minus 1 times n minus 2 times, etc. n factorial different dependency trees, right? In this one, I cannot iterate in each of them. This would be too expensive. So what are we gonna do? Of course, there are dynamic programming based methods. Okay, there are graph algorithms. There is constraint satisfaction. Okay, and there is a greedy algorithm, greedy choice of attachments. What is greedy? Well, don't try to solve it exhaustively. Okay, we will find some good enough dependency trees if you follow a greedy structure in linear time. Today we are not going to look at any of the, well, a little bit this one, not this one, but mostly this one, transition based parsing, or it's like a compiler type parsing. Okay, so this is a greedy transition based parsing. Okay, it was, I think it was developed in 1990s. Later they updated in 2000s or something, make it even simpler. Okay, a parser has a stack sigma, a buffer beta, and a set of dependency arcs A. Okay, so beta is my buffer. It holds the original sentence. Book that flight, for example. Okay, book that flight is going to be my buffer. And a stack, okay, it keeps the words that you have read. Also, it keeps some relationships, okay. And then I have a set A, which includes the dependency arcs that I have recovered. Instead of looking at this alpha, beta, and A, let's see this in an action. Maybe I will come to this later. Okay. So let's say my sentence is I ate fish. Okay. I ate fish. So at the beginning, my sigma is just root. There is nothing in it. That's how you initialize it. And my buffer is I ate fish. Okay, this is my sigma, this is my beta, and in my A I don't have anything yet. Okay, so this is what I do. There are three things that I can do. One is shift, one is left arc, one is right arc. Shift reduce parser, shift left arc and right arc. So this is first, from the start, I shift. Shift means that get one word from this buffer B beta and put it into my stack sigma. Okay, the other possibilities are reduce or arc, left arc or right arc. Okay, in this case I am not going to do that. Okay. And well, how do I know that whether I should shift or reduce? Well, I will talk about that in a few minutes. Okay, so I shifted once, I shifted second times. Okay, and when I see that I have an 8 in the buffer, now I am going to do this left arc thing. So what is it? So it is I ate fish. Looking at these two, I decided that there is a left arc between 8 and fish. Okay, there is a left arc 8 and no, it's not there. 8 and I, right? There is an 8 and I, there is a left arc, and I added to this A. See, A is added, this relationship 8 and I, it's a nominal subject. I is the nominal subject of 8, and I added to this rules, this arc set A, and I kept what? I kept okay, 8 in my in my stack, and I took I out. I is a dependent of 8. There might be more than one dependent of 8, so I am keeping 8 in this one. And in this case, all I have in my sigma buffer 8, and in my buffer fish. Okay, and I am doing shift again, 8 and shift fish, and 8 and fish is going to do a right arc. What is the difference between left arc and right arc? Left arc, right arc.
One takes the rightmost one, the other takes the leftmost.
Yeah, the relationship is always between these two. Okay, but this one, it says that the relationship is 8 is the head, I is the dependent. Okay, 8 to dependent. In this case, right arc. Okay, fish and 8. This is the head, this is the dependent. Okay, so in both cases 8 is the head, but their order are different. Left arc, right arc. So I got it. Now I have what? I have root 8, and I'm going to do another reduce right arc, and it's going to be root 8, and this one is going to root is the head, 8 is the dependent, and that will be it. So my total, how many arcs did I recover? I recovered, how many arcs did I recover? 1, 2, 3, right? 8 and I, 8 and fish, and root and 8. That's it. So this is called a shift reduce parser, and the rule for the shift and rule for the reduce is this one. Let's read this one. Does anybody know prologue? Prologue? You know prologue? Where did you know? How do you know?
Yeah.
From the PL. Okay. So these are like prologue rules. It says that if you have your sigma, if your buffer at the top of the buffer you have WI, okay, if you are A, if you are doing the shift, this is what happens. You add WI at the end of this sigma buffer, and your beta becomes this, right? Like prologue. This is shift. This doesn't tell you when to apply shift. This doesn't tell you when to apply left arc or right arc. This will just tell you how you execute these rules. Okay, let's read this one. Okay, let's read this one. This is your sigma, this is your beta, this is your A. How about this one? This is your sigma, this is your beta, and this is your A. If you are such a sigma buffer, at the top you have the WA and WJ. When you do your left arc, you add an arc from WJ to WI, an R arc, okay, and add it to your A. Remove that stuff, remove that WI from your sigma, okay, and you'll be done. For the arc I, it is almost the same thing, only thing you leave your WI in the buffer, okay, stack, and your arc is going to be WI to WJ. Okay, to the condition for finish is this. Condition for the finish is beta is just empty. There is no word to read, and on the sigma side, I have only the root. Okay, I have only the root. These are the three rules. So I told you the rules. I told you how the algorithm works, but I didn't tell you when to shift and when to left arc or right arc. You can do three things, right? Shift, left arc, or right arc. I didn't tell you how to do that. Any guesses? Can you tell me any guesses? Maybe this could be a hint. This could be a hint. Well, if you see discussion and issues at the top of your stack, you will say that, okay, issues is the head, discussion is the dependent. You could say that. But what did we say before? These are not definite rules. And am I going to write these kind of rules for all kinds of bilexical affinities? No. Again, the dependency distance, if they are close by, if they are close by, there is a dependency. No, I can't say that. So how am I gonna know that when to shift and when to make an arc? Well, it was in our case. Remember, this is a greedy approach. We are not saying that we are going to find it the perfect way. Okay, it's a greedy approach. It may fail, but still, I mean, we shouldn't take our decisions randomly.
You should try to find the verb first. Maybe.
Verb first, but in this case, the verb was the last one, right? I mean, the arc, to add an arc to the system. 8. I shifted again. Okay. Now the third time I'm not shifting it, I am going to make an arc between those. Right? And I shifted, and I'm going to make and at the last time there is the word, and verb was the last one to leave my stack. But maybe you are right. Maybe I should look for the verb first. Verb needs to be a head, and the rest of them will depend on it. But if I have to compose, remember the composed sentences? There are 2 sentences. Are there? What was the sentence? The query about the card. Are there any Koreans doing that and that, etc.? Well, the answer is okay. The answer is, the book has a very nice answer to it. Okay. Where is that answer? I read it yesterday. I was okay. Yeah, here is the answer. So when to okay. Well, how do we choose it? Well, we are going to use machine learning. We are going to say that okay. Extract the features of each word and their relationship with the others, and make a classifier. Classifier will look at the top of the stack, will look at the buffer, and it's going to make a decision. Okay, shift or reduce. Okay, shift or reduce. That's what we are going to do. But I think I need to take some break. After the break, I will continue on this. Good. Do I have enough space?
Hocam, şeyden haber geldi mi bizim okul strateji merkezinden? Hani TÜSEP için banka hesabınız açılmıştır falan.
Belki gelmiş olabilir ya, ben bir bakayım.
Bana hiçbir şey yollamadılar da ondan belki direkt size yollamış.
Bana yollamış olabilirler, evet.
Eğer yollamadılarsa...
Yolladılarsa da onlar şeye de yolluyorlar onu. TÜSEP'e.
Yollamadılarsa ben çünkü Sevin Hanım'la konuşayım.
Sen ona bir daha konuş, sen konuş, telefon etsene.
Bir şey olmaz. Tamam, bir konuşayım oluyor.
Hoca dekanlık işleri zor de.
Tamam hocam.
çalışsam yapamazdım. Sığıyor işte. Böyle başka bir şey. Ben çok çalışsam da yapamam.
Belki yıllar
Bir tane soruyu söyleyebilirsin. Çok soruyor. Bir şey.
evet.
İlerisi yaptım ama bu mesela geçen gün diyelim senin canlı bir şey söyledi. Yani hiçbir şey yapamıyorsun. Kendisi bir şey yani zaten olan bir konusu değil de kendisi portakal bir şey yapmış. Kendisi oluşturma sonra şeyler yapsa, en azından anlamaya çalışmışlar ama bir şey yapmışlar. Kendisi bir şey oluşturduğu için.
Evet, aynen. Evet, tam olarak. Ben de böyle oluyorum.
Okay, so I forgot the tangents. So I am going to write a classifier. Okay, that will. What is the input to the classifier? The input to the classifier is going to be these three data structures. Okay. This stack sigma, buffer beta, and this dependency arc A. Since we are producing this A as the output, I don't need it as an input. So the sigma and beta will be our input to the classifier. That will be it. And so out of three decisions, either shift or arc left or arc right. Okay, but there are labels for each arc. Okay, there is an arc for object, there is an arc for end subject, and etc. So there are arc types. So if there are R number of types, arc types, that means that r times 2 plus 1. What is 1? R times 2 is left arc or right arc. What is this one?
With the root? Connection with the root?
No. This is for the classifier. Classifier is going to classify our actions, either shift or left arc or right arc. There are many times different types of dependencies. That's why left arc or right arc is 2, right? So r times 2 plus 1. What is plus 1?
Shift.
Yeah, exactly, shift. For shift there is no parameter, right? It is just shift. But for the arc, I need to specify the type of the arc. Object, arc of the object, arc of root, arc of subject, and etc. Right? So that's the classifier, and there is no search involved in the simplest form. There is no search involved. That means what? If there is no search involved, that means I cannot find the ambiguities. So the first answer is going to give me. Also, if there is no look ahead, no search, okay, I may fail from time to time, but that's what we said at the beginning. Right? We said that this may not be a very good parser that can parse all kinds of trees. Since especially it is based on machine learning, but I don't want to get into details of dynamic programming, details of this dependency parsing. Okay, well, this one says that you can probably do a beam search. Does anybody know what beam search is? Beam search. Beam search is kind of a artificial intelligence search, of course. You keep 3 or 4 solutions at the same time, alternative solutions, and if you see more solutions, you eliminate out of these 3 or 4, and you always keep the 4 best solutions around, and you do your search this way. Greedy search always keeps the best solution available. The others are not the best solution. 4 best solutions, and you try to update each of them because you don't know which one is going to be the final result. So again, even if you do the beam search, it's not going to be optimal at the end because you are not exploring all possible ways of dependency parsing a given sentence. Okay, the model's accuracy is fractionally below the state of the art in dependency parsing, but it is very fast. It is linear time parsing, and the performance is good. And this is the feature vector that we are going to use. Okay, this is stack. Okay, and this is the buffer. In my buffer, okay, has good control, right? Has and good is in there, and control. So what do you think? Should we shift or should we left arc or right arc? Looking at those. Well, if you are going to give me only these 3, then maybe I should what? Has good control, right? It looks like I shifted good, and when I am reading control, now I'm going to make a decision: shift or right arc or left arc.
Left arc. Right.
It's an arc, right? Because good is the head of. Oh no. Has good control. No, maybe I should. Shouldn't I shift? Because has good control. Good control. Control is the head of good, right? Good is independent. I think I should shift in this case. Well, we don't know the exact sentence. That's why I cannot say anything like that. So what I'm saying here is this. Okay, I will have a binary feature vector that's going to indicate lots of flags. For example, the one before me is a adjective. The one before me is a WZ or etc. and etc. Or the word is a good, or the word is has, and etc. So very large, very big binary vector, and my classifier will take this vector and it's going to give me one of these actions: shift or right arc with the type, or left arc with the type. Okay, so that's how it's going to work. Again, it's a grid algorithm. It very much depends on the success of the classifier, machine learning classifier that you have, but it says that it is good enough. Great performance, linear time parsing. Okay, once we are done with the parsing, I need to measure my performance, right? How am I gonna measure the performance? She saw the video lecture. Okay, this is the golden standard. That means that that's the correct one. So how are we going to do that? Let me go over this one. Okay, so root 0, 1, 2, 3, 4, 5, these are the, okay. So 0, 2 is the root. This is the relationship is root 0, 2, right? 2, 1 is n subject. This is n subject. Okay, 3, 5 the determiner. 3, 5 is determiner. 4, 5 is nn. 4, 5 is n. Okay, noun. And 2, 5 is what is this? There is 2. Okay, 2, 5 is object. This is the golden. This is the gold data. That means that it is the ground truth. We know that this is true because somebody's parsed it. The one that I parsed out of my parser gave me this. Says that I found 0, 2, that's good. I found 2, 1, that's good. But 3, 4, the determiner, okay, 3, 4. So it says that the video is the, okay, the video is the arc. And then 4, 5 is n subject. Okay, there is a 4, 5 or 4, 5 lecture video. And then 2, 5 is the C combination. Okay, C comp. Oh, no. What is 2, 5? Lecture. Okay, this one says that the combining of two sentences. This one says the object. Okay, it looks like I got how many correct? This one is correct, right? This one is correct. Out of this one is 3, 4. Okay, 3, 4 is bad. 4, 5 is correct. The arc is correct, but the type of the arc is not correct, right? Again, here the arc is correct, but the type of arc is not correct. So depending on what you are counting, it looks like if you count the arcs as the correct or not correct, the first one is 4 out of 5 is okay. For the second one, if you're counting the arcs plus the types of the arcs, then in that case, it is only 40%. Okay, only 2 of them are correct. So that's how you measure your performance of the dependency parsing. Good. Any questions on this? Well, I mean, it is not an algorithm as elegant as the CKY parsing or the early parsing with definite rules and etc. It definitely doesn't give us any ambiguous representations. It as the name implies, greedy. What was the alternative? Alternative is checking all those n factorial number of parsings and choosing the best ones and etc. Okay, handling the non-projectivity. Of course, do you think that this algorithm can handle non-projective stuff? That means that intersecting arcs, like this, there is an arc between she and lecture, for example. It is intersecting with many arcs, or just one arc, doesn't matter. Do you think I can handle those non-projective cases? Why not?
Because when she saw the word saw,
Yeah.
she will eliminate she.
Yes, exactly. So, because when we do the shifting and arcing, okay, when you do the arc, okay, 8 fish, I remove fish. There is no way that fish can form another arc with somebody, right? It has to be with the 8. I didn't do that. So fish has to go to some left or right of the 8, okay? And there is no way that fish can form another arc over 8, over the verb. And the same thing will happen for the others. That's why this parser, this simple gradient parser, cannot handle non-projective cases. So what are we going to do with the non-projective cases? Well, we just say that we don't handle, okay, non-projective arcs. That's it. Like the context-free grammars. Okay. Use dependent formalism which only has projective representations. Context-free grammar. Okay. If you originate from context-free grammar, then everything has to be projective. Okay. Or we can say that, okay, add a few transitions that can model at least most non-projective structures. Okay, like remember the ones that I give you. Instead of saying from whom I got this book and etc. I know those kind of sentences. Check the cases for those kind of sentences and add a few extra transitions. See if this is working. Okay, so or use a graph-based algorithm. Okay, MST parser, graph-based algorithm, which doesn't assume any tree kind of structure. That will solve the problem, but these are very expensive and their performance may not be as good as you expect. Graph-based dependency parsing MST. Let me take this out. Okay. Compute a score for every possible dependency for each word. Every possible dependency. So for this big, every possible dependency, doing this requires good contextual representations. After doing this, I mean, this is just for big. I'm going to do this for the and cat and sat. So everything is connected to everything. So it's a full graph. Okay, it's going to be a full graph, and add an extra edge from each word to its highest scoring candidate, and repeat the same process for each other word. That doesn't mean that you are going to get the best one, but it doesn't care. This one doesn't care if the tree is projective or not, because I'm doing the same thing for everything, right? Same thing for every other word. Okay, this is called graph-based dependency parser. Again, machine learning based stuff. Doesn't care about any order at all. Okay, doesn't care about any order at all. Order could be anything, and this can handle projective cases too. Okay, these are some good representatives of the dependency parsers. Remember this metric and this metric. Which one do you think would produce the larger, higher results? Of course, this one, because this one counts the arcs, the correct arcs. This one arcs plus the labels, right? So these are some of the results. 94% of the cases I am doing it right. Okay. So, of course, you don't expect to do 100% correct. Why not? Because these are all human seeding problems. There is no 100% correct in NLP. There will be some disagreement between the human experts. So these are pretty good results, depending on the, of course, depending on the data set that you have. Okay, I guess that will be it for the dependency parsing. Any questions? Okay, so if there are no questions, since we started talking about machine learning, let's go to let's go to neural networks, and I am going to spend the rest of the semester doing neural networks. Okay. Today I'm going to give you some basics. After that, we will talk about more NLP stuff about neural networks. Then we'll talk about deep learning with the NLP. But today, in today's lecture, I am going to give you this name entity recognition problem. We talked about that before. This is what we are. Where is my name entity recognition? Yeah. Okay. So name entity recognition is defined like that. Task is to find and classify names in text, for example. Okay. The European Union said on Thursday it disagreed with German advice. I found, okay, European Union is a name, okay, and German is miscellaneous. It's an organization. This one is a miscellaneous. Okay, only France, which is a location, and Britain location, backed Fischler's proposal. It's a person. So you find the names and you classify them. Okay, you find the names and you classify them, and so it's a classification problem, and you are going to give classes for each word on a sentence. And most of the time, if you cannot find anything, you are going to say it's an other or other. Okay, or is other. That's called named entity recognition. Where do you think that we can use this named entity recognition? Why are we doing this? Why are we doing this?
Press report tracking. Press report means tracking.
What are you?
For companies.
For company? What? I mean, if I give this information to a company, what would they do?
Google use that. Google use that when you search for a name or an organization. There's a Wikipedia information on the right side.
Yeah, exactly. I mean, if I am looking for something, for example, I said that I like to look up, for example, İsmet İnönü, right? Just a name, okay? So wherever that happens as a name, named entity recognition name in sentences, that's an important as a name, right? There is İsmet İnönü Bulvarı in every city, right? I am not looking for İsmet İnönü Bulvarı. I am looking for İsmet İnönü as a person in those sentences. Okay? So İsmet İnönü University, İsmet İnönü Mahallesi, İsmet İnönü something, I don't care about those. All I care is as a person İsmet İnönü. İsmet İnönü was the presence of Turkey between this and that, right? So I need to mark it as a named entity and find it and say that, okay, you are talking about that. Okay. The others, this is a simple data mining or question answering or information retrieval example. Okay, information retrieval example. What are the organizations? Okay, what are the persons? What are the locations in my data set? If somebody is asking a question, what city is the capital of Brazil? Okay, so whatever you are giving as an answer out of your database, it has to be a location, right? Don't return me a person. Don't return me a organization. It has to be a location. So find all the locations in a database, and out of all those locations, choose the capital city of the Brazil, okay, using some kind of a machine learning approach anyway. Okay, so that's why we do the named entity recognition. Tracking mentions of particular entities and documents. For question answers are usually named entities. Okay, a lot of wanted information is really associations between named entities. See, when you say who is it is this guy. Okay, where it is this and this. Okay, what organization it is this. So the questions are usually those, and the relationship between those, like the name, like the dependency relationship, is something that is important. That's why we do named entity recognition. And when we are doing this machine learning approach or neural network approach to handle the NLP problems, this will be the first example that we are going to look at, named entity recognition. Okay, let's go back to the beginning of the chapter and let's do that. Machine learning, how many of you did you take machine learning course? You are taking it, or you took it? Are we offering it this semester? No, next semester, I guess. Okay, that's an important course. Just take that course. It is important. Important area of the artificial intelligence, and in NLP we use it a lot. Let's say I have a problem. Problem is this. Okay, I have many cars. I am a dealer, car dealer. Araba alıp satıcısıyım, tamam mı? I like to write a classifier that tells me which cars should I buy and which cars should I not buy. Okay, so I have only two things to know about the car: car's age and car's price. Okay, if the price is too high, I don't buy that car because it's too expensive. Okay, maybe I should draw this. I should redraw this. Erase it. Okay. This is car's price and this is car's age. Okay. If the price is right, okay, if the price is right, very cheap car, but it is old, I would buy it, right? So I would buy this one. I would also buy very young, brand new car, even though it is expensive, right? I would buy it. But I would not buy a car which is both expensive and old, right? I would not buy it. I would not buy this car either. I would not buy this car. It looks like I would buy it. Okay? It looks like there is a line that separates the cars that I buy and the cars that I would not buy, right? So so I have these 1, 2, 3, 10 points, right? I have these 10 points and I can represent each of them like a vector, right? This one is age is 20 years, but the price is 30,000 liras. Well, for 30,000 liras, I would buy any car as long as it runs, right? I would buy it. So this is it. This one is, it is just brand new, but it is 600,000 liras, but I would buy that too. Okay, but I am not going to buy this one. I am not going to buy that one. It will be, let's say, it is 0 years old, but it is 5 million Turkish liras. It might be a nice car, but as a car dealer, if I buy it, I cannot sell it. Okay, so I have all these data. I marked them before, like I sat down one day. I marked them one by one, or 100 of them. So let's say I have 100 points, 100 vectors like this, and for each one, I know if I should buy it or not buy it. Okay, yes or no. So I made this. Xi is my vectors, okay. Yi is my label. For this one, 2 years old and 100,000 Turkish liras, I would buy it. 10 years old and 80,000 Turkish liras, I don't buy it. Okay, so I have this set. Xi my inputs, okay. Inputs are my vectors, like two-dimensional vectors, or sometimes my inputs are my words, okay. I have 10 words as an input, or sometimes my inputs are many sentences or the documents, okay. How do I represent words or sentences or documents? It's something different. You know how to represent words, right? Using word to vec or some other approach. How to represent sentences? Again, maybe a vector form. Or we don't care yet. But all the thing is, all I'm saying is that my inputs are my vectors, okay, and my yi's are my labels. In my case, yes or no, buy or not buy. Or in case of sentences, if I have a sentence as an input, sentiment, is this a positive sentence or negative sentence, and etc. In case of words, if my input is a word, maybe named entity recognition is a good example. Is this word a location? Is this word an organization? Is this word a person? Right. So those are my things. Okay, those are my things. So maybe later I am going to discuss how I am going to input this multi-word sentence and etc. But for now, you just know that these X's and Y's are my inputs and labels. And usually for the efendim, teşekkürler Erman Bey. Şu anda bir dersteyim. Acil mi? 10.30'dan sonra. İyi çalışmalar. Okay, so that's the basic input. So what we are going to do is let's try to find a line that separate these no buys from these buys. Okay, what kind of line I can find out of these? So how do I represent a line? A line is represented using just two numbers, right? How do you represent lines? You will say a line is represented mx plus b equal to y, right? So x and y is my variables. M and b is just two numbers. Okay, I can get just two numbers out of these and represent a line that way. So out of all these 100 points, some of them are correct, some of them are yeses and some of them are no's. I need to find a line that would separate this case, that would separate this space into two. Once you find these m and b values, whenever a new car comes in, you would put that new car in the space. Let's say I put it in here and compare it with this line. If it is below the line, that means that I am going to buy it. If it is above the line, that means that I am not going to buy it. Okay, I am not going to buy it. That will be it. Okay, so that's the basics of this classification. If my classification is a linear classification, later we are going to find examples of how to do this without any linear constraints. Okay, that's it. Okay, so the training data is this, and simple illustration, I am going to separate this space into two good ones, yeses and nos, right? And find a line that will separate this space into two. Question for you. How do you separate this space into two so that these green stay in the green area and reds are always in the red area? How are you going to find it? Maybe before I'm making you think too hard, the answer is, well, you can't. Okay? There is no line that will separate this space into two, okay, perfectly. So on one side, there will be some reds where it shouldn't be. On the other side, there will be some greens where they shouldn't be, right? So we call this training error, okay? In our training error, whatever I do, I cannot put these green dots in the correct part of the picture, okay? You might say that, well, if I have more than one line to make this decision, maybe I can do it better. Well, I might say, well, maybe you are right, but the problem will remain there, okay? Even 3 lines may not be enough sometimes, okay? So the training error will not be 0, almost always. 0 training is something that we don't like much, but the training error of a few percent, like 5%, or 10% is acceptable and often desired, okay? It is often desired. So don't try to find a line, okay? Don't try to find a line that will separate this space into perfect two yeses and nos, okay? So it's going to be a little bit noisy. What did we say about the artificial intelligence problem? We said that artificial intelligence problems, they usually don't have 100% correct solutions. We say that we are good enough. That's it. We are good enough. So you are not going to find a perfect line that will separate cars to buy and cars not to buy. Because if you can find it, there is no problem with the car dealership then. I am always making perfect decisions using this line, right? Unfortunately, there will not be any machine learning solutions that will give you 100% correct solutions. But statistically, it's going to tell you that, okay, I am going to do as good as a human car dealer. That's what I'm going to do, okay? So usually this is what we do to deal with this problem. We have, let's say, 2 classes, yes class and no class, okay? For each class, I produce these 2 numbers, W11 and W12, class number 1, 2 weights. Given this 2-dimensional feature, like the car's age and car's price, I multiply it with these 2 numbers, okay? That will give me how much I like the class number 1. The second one is going to give me how much I like the class number 2, okay? How much I like the class number 2. And I like to convert all that information to probability, okay? At what percent I like class number 1 and what percent class I like class number 2. The probabilities of these classes should add up to 1.0. For that, that's what we are going to do. We are going to use softmax or logistic regression. Okay, that's what we are going to do, and this is the formula. Don't make this formula confuse you or make you. Don't let it scare you. It is a simple formula actually, and I am going to look at it in a few minutes right after the break because I need to take a break first. Okay, break. Where is my Attendance. Peki. Herkes silahlı mı arkadaşlar? Nasıl atladı sen oradan ya? Kalemin yok mu? Şu arkadaki pencereyi açabilir miyiz ya? Bir zahmet.
Zaten o kadar oluyor ki harbi çekiyor ya.
Yoksa draft olması çok önemli.
Sadece bir saatlik buna bir arkadaşım bana verdi. Bir şey dinlemek istedi. Çünkü o da beceremiyor. Ben de kayıtlı bir şekilde çalışıyorum. Bundan sonrası yapacağım yani. Adım var. Adamın şeylerini istedi benden. Ben 2 saat onlarla uğraştım. Ama yani çok zor geldi. Nasıl bir yapacağım araştırıyorum, işler izliyorum, onların hikayelerini çalışıyorum. Benim çok hoşuma gitti, ne oldu? Hayır, kendisi. Burası biraz burası biraz garip ama şu güzel. Wallpaper bile daha yapmak. Resim var neyse ki. Daha konuşalım. Çekelim lütfen. Dur ben ilk kez çektim. Nereden bulacağım? Portrait effect değil. Sen angle. Ya alırım diye düşündüm. Yani geçen sınavı çünkü yaptım. Geçen sınavı yaptım sürekli. Ondan öncekini yaptım tamam. Ama bu sene alakası yok. Aynen. Burayı ben de verdim. Şu an bunu yapıyorum. Tuzak yapmış. Ben de. Çok zor yapmış. Bence de müzik yapabilirim ya. Nasıl olur? Bilmiyorum ki. Ben neyim hiç Türkiye'ye biraz önce açtım vardı değil mi? Öyle bir şey oldu mu? Soğutkenler var.
Yani doğru. Ben 3 pas
Ya da kendi karakter değiştirir. Şimdi mi? Gerçekten bir çocuk ya. Benim bir arkadaşım var. Kırlarda sürekli çocuk bir de erkek bir falan. Ben de diyorum saçmalama. Perşembe organizasyonu 11'de yani 15 Haziran. Yani organizasyona bağlı. Yazık oldu oraya. Nasıl lazım? Tamam. Öyle yaparsan büyük bir olacak.
hocam oturduk yapacağım. Okay, so this is what we are going to do. Keep this line thing in your somewhere in your head. We are going to return to it, but the thing is that we are going to represent, okay, each dot as a two-dimensional point. Okay, each dot is a two-dimensional point, and for each class, I have two classes here: yes class and no class, right? For each class, I will have two weight numbers, W11 and W12 is the class number 1, and this is the class number 2, okay? So, given this my feature vector, the car's age and car's price, I will multiply it with these weights for the class number 1, and I will multiply it with these two for the class number 2. So, it's going to, this matrix multiplication is going to produce me two scores, right? S1 and S2. Okay, S1 and S2, and when I do this, okay, two scores again. This number is a real number that can change from minus infinity to plus infinity, right? And this number is the same thing too. So, but I don't want to use numbers very, very small and very, very big. I like to represent the scores for each class, okay? This multiplication will give me the score for the class number 1. This one is going to give me a score for the class number 2. I like to represent them as probabilities, and this is how I'm going to do it. Okay. So this is a dot product, right? This is just multiply these two numbers with these two numbers is a dot product. Dot product can give you a number between minus infinity to plus infinity, and if I take the exponentiation of it, exponentiation, that means what? Let me try to write it like here: e to the power w11 times x1 plus w12 times x2. Okay, it's going to give me a positive number. Remember, this is the e to the power x, right? E to the power x is like this. For the minus infinity, e to the minus infinity is 0, e to the 0 is 1, e to the 1 is e, and it goes like that. So whatever this number is x is, e to the x is a positive number, right? This is something that we like. Okay, so everything is positive, but again, it can change from 0 to plus infinity. 0 to plus infinity is something that we don't like. For that, we are going to do this. For all the classes, make this calculation. Okay. For the class that I like to calculate the probability of, put it to the upper side of this fraction sign, and it should give you a number between 0 and 1. Why? Because when c becomes y, the upper side and lower side will be the same. The rest of them will be calculated and added up. So this number, this division, is going to be between 0 and 1. This is called softmax. If you have more than two classes, softmax. If you have just two classes, it is just logistic regression, 0 and 1. Okay, 0 and 1 will be logistic regression, and it's a standard thing. It has a number of nice features, because I am using, you might say that, why aren't you taking 10 to the power x? 10 to the power is going to do the same thing, right? Everything will be positive. Does anybody know why we are using e to the power x instead of 10 to the power x? Anybody? You know it? You know it's a logistic regression, right? You know, again, why do we prefer e to the power x? Because we like the number e. Why do we like it? Because if you take the derivative of it, it's the same thing, right? What is the feature? What is the nice thing about e? The slope of this curve is equal to e to the power x at that point. Okay, this is the slope. Okay, so the slope of it. So why do we like taking the derivative of the e to the power x? Because we are going to optimize something later. Okay, we are going to take derivatives of it. We are going to optimize something later. That's why we like working with the natural logarithms and the number e. Okay, so we show this whole thing. Okay, given a feature vector, a car's price and age, multiply it with these four numbers, get these scores, and put these scores inside this formula. So it's going to give you 30% chance of buying it and 70% chance of not buying it. Okay, so I made my decision. So it's not a definite decision. It doesn't say definitely buy or no, don't buy it. Okay, it says 70% I am giving you buy. Okay, so it has a confidence number in it too. It's not just buy, 70% buy or 30% buy, not buy, etc. Okay, so we try to show this. We try to show this using the neural network notation like this. Okay, this is my input x1 or cars age and cars price. Okay, this is my input, this is my neural network. Okay, this is my neural network, and I get these. And is this too early? Maybe let's delay the discussion for this one a few more minutes. I will come to this one. I will draw the diagram for you later, a bit later, because I am taking some shortcuts for now. Okay, so details of softmax classifier. Okay, that's what we are doing. We say, okay, for this one softmax classifier, we take the white row of W. Remember, W is a matrix of numbers, and the number of rows of this W is the number of classes. Okay, and X is just a feature vector. Okay, take the white row of W and multiply with that row with X. So if W is from 1 to C rows, okay, multiply that row with this feature vector X. This is my vector, feature vector X, and it's going to give you a number. It's a scalar number, right? Just a number, and put that number into this e to the power that number, and all the, what is this? This is the multiplication of all the rows with that X feature vector, and that's going to give you this softmax value of that one. Okay, so training with softmax and cross entropy. So this is what we are going to do. What kind of W values should I choose? What kind of W values should I choose? Because I don't know the W values yet. This is a training case. This is how the machine learning works. You determine those W values from somewhere. Okay, then you run your numbers through this matrix, do all that calculation, and make your decision. But where do those numbers come from? For that one, we are going to do this. Okay, we are going to do this. For each training example XY, our objective is to maximize the probability of the correct class. Given this car's price and car's age, okay, I know if I am going to buy it or not buy it in the training case, not the run case or the test case. I know that I like to maximize the probability of the correct class. If it's a buy, I like the probability to be 1.0 for the buy, If it is no buy, I like its probability to be 0. Okay. For that, I am going to calculate this one. What is this? Remember the softmax thing? I take the minus log of it. Well, what is this? This is equivalent to minimizing the negative log probability of that class. Okay? This is going to be between 0 and 1. By the way, this is the logarithm of it, right? E to the power is, logarithm is just the inverse of it, right? Inverse of the e to the power x. It's the logarithm of x. So the number that I'm going to give you, is this one will produce values. This one will produce values between 0 and 1. And this is how it behaves, this 0 and 1, right? From 0 to 1 is going to produce numbers minus infinity to the 0, right? To 0. If I take the minus of it, it's going to be plus infinity to 0. Okay, minus log likelihood. Using log probability converts our objective function to sums, which is easier to work with on paper and in implementation. And what we mean by this will be clear because remember, with this one I am measuring a probability. Let's say I have n cases, okay, from 1 to n. For x1, I have a, okay, for a 0-year-old car, the price is k, okay, for x2, etc. Each one will give me a probability, okay, and I like those probabilities to be as high as possible. But I like to have the total probability, which is the multiplication of all those probabilities, to be the highest. If all of them are 1.0s, I am very good, I am fine. But I know that they won't be 1.0s, all of them, okay? If I multiply all those numbers between 0 and 1, I will end up obtaining a very small number, because if you multiply 100 numbers between 0 and 1, they will get smaller and smaller and smaller, and for a computer environment, I will be underflowing it. That's why we do this shortcut, taking the logarithm of all those multiplications, and at the end, they will be added instead of multiplied. Because remember, logarithm of something multiplied is addition of those, right? So I'm going to do that too. And this is what we are going to do. So take the probability of correct class, okay, true probability distribution, and take the minus log likelihood of my estimation, multiply and add them. It will be the same as multiplying them together, all those probabilities. And this probably is called cross entropy, and is from information theory. They have a theory under it, behind it. I am not going to talk much about it, but we say that if you optimize, if you make this value optimized, then you have a good training phase. You have determined all of your W numbers correctly, or at least good enough, because your entropy is now optimal or close to optimal. So let's look at this formula now. We already looked at this one. This is the minus log of my probability. My probability is going to be between 0 and 1. If probability 0 is going to be minus infinity, right? So it is going to be plus infinity. If probability is 1.0, it's going to be 0, okay? It's going to be 0, like that one, okay? And I am taking the minus of it. We don't like very probability 0. Probability 0 is going to produce minus infinity something. I take the minus, plus infinity. We like probability 1s. It's going to be 0 in this case. So what do I like? I like this number to be as small as possible. So I like this to be as small as possible too. So the minimize the entropy, cross entropy. But how about this? How about this? PC, true probability of distribution. Okay, true probability of the distribution. If my true probability is going to be either 0 or 1, right? I mean, what is the probability of this one? It is 1.0 because I know that it is yes. What is the negative probability of this one, or the probability of being no to this one? It is 1.0. Or positive probability of this one, it is 0.0. What I am saying here is that this one is either going to be 0 or 1. For the zeros, this will cancel this out. For the ones, I will add them together. Okay, I will add them together. For a given class set, let's say I have n classes, or maybe m classes. For a class set of m classes, only one of them is 1, and that one will count my calculation for the softmax, this one. Okay, if I add them up, all of them up, I expect this number to be as small as possible. Okay, that's called the cross entropy. If you minimize the cross entropy while you are training your data, you are doing something good. You are doing something optimal according to information theory. So basically, if I go back to the beginning, you are given n training instances like this. You are given n training instances like that. Okay, you are saying that to be able to divide this space into 2 linearly, I need to find these 4 numbers. And to be able to find those 4 numbers, I need to calculate the probability of each dot on this plane and find such 4 numbers so that, okay, this entropy formula is minimum. Okay, so how are we gonna find such numbers? I think we tried this, we did this, something similar to this, using our in our chapter about word to vec, calculating those word vector numbers. Remember, we take the derivative and we try to push those numbers to some direction that it makes this loss value or the cross entropy minimum. Okay, so that's what we are going to do. Take the minus log of this calculation, probability calculation, and add them up, minus 1 of them. Okay, pick w, y, j's in a way that makes this cross entropy, or that makes this loss value as small as possible. Okay, as small as possible. So that's the basic training algorithm. That's the basic test time, runtime algorithm for the neural network. For a neural network, I'm going to talk about why we are calling them neural networks. For a neural network, the task is finding these y's and j's for given the training set. Okay, good. So traditional maximum likelihood optimization. Let's traditional ML optimization. I'm not going to tell you what ML is. I told you, but I'm not going to explain it. So for a general machine learning, theta usually only consists of columns of W. Each W is it belongs to a class, okay, and each W contains a certain number of elements. In this case, D number of elements, D-dimensional world. Okay, in this case, it's a 2-dimensional world. Each W is going to contain 2 elements in it. There are C classes. Okay, if I multiply my input with this parameter set, I will get my softmax results. Okay, so the traditional ML optimization will take the derivative of these values, W's, okay, their change, and push them towards a value that will make this loss smaller and smaller. I know how to calculate these. These will be calculated using this notation, and that's it. That will be it. There is some e in it, and take the derivative of them, push them towards the minimum. Okay, that's what we call a neural network classifier. Okay, so the same problem. Whatever you do, if you are going to use a single line, you will not get any of these green dots correctly. They will always fail. Okay, or some of them correctly, some of them wrong. There is no way that you can correctly classify them using a single line. But if I use something like this, it will be okay, right? It's not a line, but it's a curve, and curve is like this. Okay, this is my curve. Whatever underside of this curve is true, in the other side it is false. But this is not a line. How am I going to define this line? Neural networks say that, okay, you don't have to use these W's in a single shot. Take this output of a W, okay, this multiplication, feed it to another W, okay. So take these values. Where are my values? Okay, where are my values? Where are they? Yeah. Take these values, multiply it with your inputs. They will produce another set of vectors, and take that vector as another input to another network and feed it that way. And at the end, you are going to obtain other stuff. What does that mean? Each layer of input is going to produce another line set, and these line sets, when they come together, it will produce a curve like that. It is not going to be an exact curve, but it's going to be a curve like this: line, line, line, line, line, like that. Okay, so a number of line combinations, so that makes multi-layer neural network. Okay, that's going to be even more difficult, but I'm not going to talk about that difficulty yet. Okay, so up to now I kept talking about cars and their prices and buying and not buying. Obviously, this class is not about cars or buying or selling. This class is about natural language processing. So what are we gonna do with these neural networks, with the natural language processing? Remember what we said about the words. We can represent words using vectors, right? Word2Vec did that. But Word2Vec, the goal of the Word2Vec is to represent words such that the syntax-wise or semantic-wise similar words will have similar vectors, right? That's what we did. Now I am saying that I am going to take a word. I am going to take a words input, words vector. Let's say vector of, let's say, a book. This is 200 dimensional vector. I am going to multiply this with a 200 by 200, okay, or maybe 200 by 10 matrix, 200 by 10 matrix. It has 10 rows and 200. It has, let me do it right. If this one has 200 lines in it, This one has 200 columns and 10 rows. Okay, I am going to multiply this 10 by 200 matrix with this one, and it's going to produce how many numbers? 10 numbers in it, right? 10 numbers. Each one will be a probability. And I like to think this probability as named entity recognition class probabilities. Okay, this one is going to be, let's say, location, person, date, proper noun, etc. At the end, I have other. Okay, I will give you this word. I will multiply it with this matrix, and that will produce me this probability distribution. Okay, probability distribution. And some people say that, well, this is a chaining problem, right? Find these W's first. Find these W's first. Okay, and when you do this, you are going to get the probabilities out. And some people say that, where did we get this word-to-vec vectors? Why don't we find these vectors along with this 10 by 200 numbers too? This is a matrix to determine the named entity classes. This is a vector that I have obtained. This is a vector that I have obtained from word-to-vec calculation. Why don't we do this at the same time? Okay, so our word vector assignment problem becomes learning the word vectors plus the named entity recognition problem at the same time. Okay, so what did I do? I learned word vectors specific for this problem, named entity recognition problem. Okay, that's what I did. So common in NLP, we learn both W and word vectors X. We learn both conventional parameters and representations at the same time. Of course, I don't start from the scratch. I start from the word vectors that we have learned before in an unsupervised way. Then I introduce this problem of named entity recognition. Okay, that's what I do. Of course, this is a very large number of parameters. If I have 40,000 words in Turkish, for each one I need 200 dimensions, and then I have 10 times 200 dimensions here too, numbers here too. It's a very large search space. But if you solve it in an efficient way, your results will be better than finding them separately. Okay, classification with word vectors. Okay, I kept talking about neural computation, neural networks, but I didn't talk about why we are doing those. Okay, this is a human brain cell, neuron. Okay, there is only one neuron. Okay, this is a neuron. Let me try to. This is one neuron. Okay, this is the center of the whole cell. Okay, these are axons, these are dendrites. I'm going to talk about what they are actually. Okay, basically what they do is they take inputs from this end. Okay, so they are touching to each other, right? These are the inputs for this neuron. Each input is multiplied by a different weight. In this case, electricity is transmitted between the cells. The amount of electricity transmitted from this cell to this cell is controlled by the chemical around here, the type of the chemical and the chemical structure of this connection. If the connection is strong, then the whole current is drawn in that location. If the connection is loose, then not much current is drawn. Okay, and basically that means that I am multiplying my input with something, a multiplication, and at this end it outputs some value depending my inputs. Okay, then we said that why don't we represent a neuron like this? These are my inputs. Okay, this one will take each of that input and will multiply each input with a W. Okay, this is x0, x1, x2, xn from 1 to n. This is I. Okay, so I am multiplying each input with a W, and the addition will be outputted as my result. That's what I did, right? Remember, this one is my multiplication of the input with the lines. Okay, so basically the motivation came from the human brain cells in 1950s, 40s. Later, we gave up imitating whatever we are doing in our brain. We said that, okay, I'm going to formalize it this way and that way, that way. The main motivation was from the brain cells, but later, for the upper level structure of these neural networks, we don't follow the human brain much. Okay, all we are saying that neural networks are learning these W's that correspond to weights for each node, for each human cell or the artificial neural cell. Okay, so don't let this neural thing confuse you. We are not doing much about human brain here. All we are doing is finding these numbers for a given data set. Okay, that's what we are doing. These are inputs. Multiply them with W's. Okay, add them up and output them using a function like this. Usually we use a function like this one. Can you guess what we are doing with this one? E to the power minus c. Remember the function e? Why did I do that? Okay, this is function e, right? The red one is function e. Green one is function e to the minus x. Okay, this is e to the z. This is e to the minus z. Okay, if I add 1 to it and divide it by 1, okay, you are going to get something like, what would you get with this one? What would be the highest value that FC can take? What? If this one is 0, then it's going to be 1, right? If this one is 0, that's going to be a 1. If this one is a very, very big value, then it's going to be 0, right? At what point is going to be 1? Whenever it is 0, right? Whenever it is 0, whenever this one is 0. So when is this 0? E to the minus z. When z is infinite, right? So it's going to be in there. So when is this going to be? So here it is 1. When this value is very, very, very big, then it's going to be 0, right? Then at one end it's going to be this, and at one end it's going to be that. So what am I looking at? It is with this green, with this blue line. Whatever you do with this z, it's going to be between 0 and 1, like a probability, right? It's going to be between 0 and 1. And if I am going to give you this, it will be 0.5, this one, because it's going to be, when this is 1, it's going to be 0.5. You might say that, why are we using this? Because, I mean, if I am going to make this between 0 and 1, I have already this logistic regression, right? Where is my logistic regression thing? Okay, I have already this. Okay, this one is very similar to that. in that case, there is only one class, either you or either this or not. This one has many classes. Okay, so softmax logistic regression is the same thing. Softmax is, okay, if I have many classes, more than one class. Logistic regression is, okay, if you have a single class, either you belong to it or not. Okay, so there is a single probability. This one is good for measuring single probability. What did I say about the neurons? It just, if I like it, then I make a 1 out. If I don't like it, I don't produce anything, 0. And this is what it does. Okay. And a neural network is this. I have neurons, I have other neurons. Output of these neurons are fed to the other neurons. I am not talking about anything different than what I talked about before. Again, this one has weights and weights. 1, 2, 3, 4. This one has 1, 2, 3, 4 weights. 1, 2, 3, 4 weights, and 1, 2, 3, 4 weights. So if I put them together, it's going to be 4 by 3 matrix for this layer. Okay. Again, remember what I said before. It's going to be a matrix of numbers. It will be a 4 by 3 matrix, and each one is doing a multiplication and addition. And if I put another layer after that one, if I put if I put another layer after that one, it will be, each one is a line. This one is producing a combination of lines. Okay, before my time runs out, maybe I can talk about these next week, but I like to talk about what are we going to do with this case, named entity recognition, so that when we come back, at least we have something about NLP. Okay, so this is our problem. This is what we are going to do. Okay, Foreign Ministry spokesman Shen Guofang told Reuters that something. This is an organization, person, organization. These are O's. Okay, others. Okay. By the way, this is not an easy problem. By just looking at the word itself, you cannot say if it's a person or not. Let's look at this one. For example, when you say First National Bank is the name of the bank, commercial bank, right? So First National Bank is the organization. You should know that, okay? Future School of Fort Smith, maybe this is a place too, right? You know what Charles Schwab is? It's a financial institution. But that financial institution is named after this guy, Charles Schwab. Okay? Name of the person is Charles Schwab, who founded that institution. But in this case, I am talking about the institution Charles Schwab. Okay? That's why it's not an easy problem. It's a difficult problem, especially solving it at a high rate. So that's what I am going to do. Museums in Paris are amazing. That's the sentence. And I like to assign a tag or named entity class to this Paris keyword, the word Paris. Paris is a location, could be a location. Sometimes we use Paris as a name. Some people has name Paris, right? It could be a name too. Okay. So my input to my network will be, let's say my words are 4-dimensional vectors. 4-dimensional vector museum, 4-dimensional vector in Paris, and are and amazing. I am going to give this 20 numbers to my network, and I like to assign a named entity class to this vector. Okay, so it is 5 times D. 5 is 1, 2, 3, 4, 5. 5 words. D is the dimensionality of the word vector. This will be my input, and this will be my input, and this will be my output. Okay, let's try to see what we are doing here. X is my input. I am going to multiply X with a W. So tell me what is the size of W? Okay, my input is going to be 20 dimension vector, and it says that you are going to give me, this one is connected to this one, like those. Each of those are connected to this one. Okay, each of them. Also, each of them are connected to this one too. Okay, and let me draw another one, and each one is connected to will be connected to this one too. So each node here will have 20 inputs, okay, 20 W's. I have 8 of them, so there will be 8, okay, times 20 numbers in this layer here. Okay, that's why W is 8 by 20. Okay, but after that, this one will be connected to this one, right? Okay, so there are 8 W's here between this and that. This is the first layer, this is the second layer. And if I train all those W's correctly, when I feed this vector in, at the other end, I am going to get the correct named entity class. It's going to be person or location. Okay, so that's what we are going to do. To sum up a little bit, because I'm in the middle of telling this story about the neural networks for NLP. I didn't finish this up yet. Next week I'm going to finish it up. To sum up, you already know how to assign vectors to words. Now I am going to use those vectors to make decisions about the functions of those words in sentences, such as part of speech tags, okay, or named entity recognition classes, or the sentiment for the whole sentence, positive sentiments or negative sentiments. That's what I am trying to do. Okay, good. Any questions so far? So watch the video that I'm going to add for this class next week, and next week we are going to continue, and we are going to see how we are doing that optimization, the optimization of the neural network for the parameters. Okay, I'll see you next week.